Rate equations. Now, the thing about rate equations is it's actually a simple topic. Now, these flashcards go through all the key information. Then there's practicals, and then there's the calculation aspect of it. So, what do rate equations link? Tell you how rate is affected by concentration reactants, links reaction rates to reactant concentrations. Tells you how rate is affected by the concentration of reactants. You don't need to know that. You honestly do not need to know that. Not on the spec. Continuous monitoring, you do need to know this is continuous monitoring when you follow a reaction to the end by recording the amount of product you have at regular intervals, and you measure rate of reaction by continuous monitoring. Initial rate of reaction, the rate at the start of the reaction, find it from concentration time graph by calculating the gradient of tangent at time equals 0. K gets bigger as you increase the temperature because there's increasing number of collisions between the molecules of the reactants. The concentration of reactants and order stays the same, and therefore K must increase for the reaction to balance, rate equation to balance. Rate constant K, a number that links the rate of reaction to concentration of reactants. The bigger the value of K, faster the reaction. Order of reaction, the power to which the concentration of reactant is raised to in the rate equation. The power to which the concentration of reactant is raised to in the rate equation. Initial rates method, we repeat experiments several times using different initial concentration of reactants. Calculate initial rate of experiment and see how initial concentration affect initial rates to figure out order for each reactant and then work out the rate equation. Now I'm going to skip these graphs. They're more like things that I guess you should stick them up on the wall and just read them every day, or today, tomorrow, Monday. Rate determining step is the slowest step in a multi-step reaction, and if the reactants appear in the rate equation, they must affect the rate. So this reactant, and this is really, really, really important, or something derived from it must be in the rate determining step. Because so it could be, identify the rate determining step, and you would have, I don't know, something, but you would then realize, oh, this mechanism occurred. So then something derived from it could also be in the rate determining step, and that's why that's in the rate determining step. The order of reaction with respect to reactant shows number of molecules. Again, that's not the order of reaction. I just went through that. Did I not just go through it? Order of reaction, yeah. The power to which concentration reactant is raised to in the rate equation. And if I just pull out my phone, 1 second, guys. This is rate equations, which is here. So you need to be able to define the terms order of reaction and rate constant. Okay, perfect. So yeah, this is not useful because I just went through order of reaction. I just went through that. I don't know why I did that twice. Yeah, order of reaction, the power to which the concentration of reactant is raised to in the rate equation. Arrhenius equation in logarithmic form, ln k equals ln a minus e over rt. To create Arrhenius plot, we plot 1 over k against ln k against 1 over t, ln k against 1 over t, and the gradient of the Arrhenius plot gradient is minus e over r. As temperature increases, K increases, temperature increases, more reactant particles react, and therefore reaction rate must increase. K equals AE to the power minus EA over RT. Arrhenius equation shows how the rate constant K varies with temperature and activation energy. As EA gets bigger, K gets smaller. As the reaction has high activation energy, not many reactant particles react, therefore slow rate.